Hey there, my name is Zakaria, I'm a mechanical engineering graduate, and today I will be explaining how I simulated a DRS in my 2-month summer internship. Mostly known for its use in Formula 1, a drag reduction system is a solution that provides the best performance a car's rear wing can offer, providing high downforce at corners and reducing drag at high-speed rates. Wait. Downforce? Drag? What's all this stuff? Okay, let me explain. To go back on the role of the rear wing, it first needs to diffuse air in order to reduce turbulence behind the car. I will explain this in the next slide. Second, it needs to generate downforce in order to improve grip, since more downforce means more friction between the tire and the road. The more friction we have, the more grip we have, and therefore we could turn corners at higher speeds, improving our lap time. Here you can see the photo of a Porsche 911 in a wind tunnel. The lines that the smoke will follow are streamlines of our flow. Normally, without a rear wing, air would slow down and make little turbulences behind the car, and this generates low pressure zones, reduce the car speed drastically. That's why by using a rear wing, the air is deflected without creating the zones of low pressure. Now let's understand understeer. The yellow vector is the force of the rear wheels on the car. The red vector is the force of the front wheels. The blue vector is the side component of the sum of these two vectors. If you don't have enough grip, then we cannot make the turn and the car will understeer. These are the aerodynamic forces applied on the rear wing. The resulting force is the force that the air applies on the rear wing. What we call downforce is the vertical component of it, and drag is the horizontal component, which basically means that drag is what reduces the speed of our car since it's opposite to the movement of the car. What you can see in the Formula 1 technology is that they are allowed to use a drag reduction system in the straight lines. Since a closed rear wing means a lot of grip, a lot of downforce, but it's only useful in the corners. Now that you understand what's downforce, you understand that a high downforce rear wing is good for cornering at high speeds. But great downforce comes with great drag. So we need to minimize drag, especially in the straight lines where we don't need downforce that much. In order to simulate the airflow around the wing, we will talk about my favorite subject, which is CFD, Computational Fluid Dynamics. You can watch my other video for an introduction to computer-aided engineering. But in our case, CFD is a very powerful tool to solve multivariable partial differential equations. Whoa, I went too far with the math there. Well, basically, your computer is going to calculate the airflow around a complex geometry using different numerical methods. Finally, the results will give us a prediction to how the air will behave in real life. In CFD or numerical simulations in general, we need 3 programs: a preprocessor, a processor, and a postprocessor. Most softwares have the 3 built in, but in my case, I use an open source program called OpenFOAM. It has its own preprocessor built in it, so you have the preprocessor and the processor, and you will need to find a third-party postprocessor. In my internship, I was lucky enough to be mentored by experienced engineers with the preprocessor called ANSA. This is my workflow in my internship. First of all, I did a bibliography and did my research on the subject. Then I went to SolidWorks to do the CAD of the rear wing and provide myself with 2 models, a 2D model and a 3D model. Next, we would need to go to meshing, so I use the preprocessor called ANSA to mesh my simulation. And in order to solve it, I used OpenFOAM, an open source CFD program that allows you to run multiple simulations with high accuracy given a good enough preparation. Now, OpenFOAM comes without a graphical user interface, so it's kind of complicated for beginners to understand it and start using it. But once you get used to the C code, you can basically make something super customized and very detailed to the physical problem you're trying to solve. In the end, in order to visualize the results of the calculations, I used ParaView, which is also an open source program that allows you to post-process your results and view the aerodynamic forces, calculate the integrals of pressures, etc., etc. For the geometry of the rear wing, we could use airfoils that are used in planes, for example the NACA 2412 series, or the Benzing 135-105, which is an airfoil that's also used in FSAE, a Formula Student competition held abroad. Lastly, we need to flip the airfoil since in a normal plane, the wing provides vertical force called lift force, and when we mirror it about a horizontal line, we get a down vector called down force. This is an example of the CAD models I did. On the left you see the 2D model, and on the right you see the model with the DRS open and then with the DRS closed. Next we did the meshing with a structured mesh and also using boundary layer refinement. This allows us to capture the real movement of the air and the real behavior of air around the rear wing. The precision and the quality of the mesh is highly influential to the results you're gonna get of the CFD simulation. That is why this is a great and very important part of the simulation or in your workflow process. Next is the domain. We took 1 meter to the right of the model, 1 meter to the left, 1 to the front, 2 meters behind it in order to capture the turbulences, as well as 1 meter above and half a meter below. This will allow us to put our wing in an environment where we consider that outside of the environment the air is unaffected by the presence of the rear wing. You can see the comparison between the tetra meshing and the hexa interior meshing algorithms. One is structured and looks clean, but the other is less structured. The main difference is the time taken to generate the Tetra Rapid, which is really fast compared to the Hexa interior. And not all software can provide you with a really good quality mesh like the right one. Finally, the CFD simulation. OpenFOAM is a very special program that doesn't use a graphical user interface, and the simulations are basically folders like this. The zero folder contains initial conditions like velocity and pressure, the constant folder contains the boundary conditions, and the system folder contains simulation settings such as the solver type, the total simulation time, the delta t increment of time, as well as the max iterations allowed, etc. Then we have the visualization file to open with ParaView. ParaView next allows us to visualize the results through a color-coded spectrum. It calculates forces and allows us to visualize streamlines and pressure clouds. On the right, you can clearly see the difference between the DRS closed and the DRS open simulations. You can see that the air slows less when the DRS is open at 250 km an hour. The yellow zones are slower than the red zones. For our 3D model, you can see that the pressure is higher than the atmospheric pressure, P0, which is in orange or in white. The red parts are where the pressure is way higher, and the blue parts are where the pressure is lower. Since we have more pressure on the top layer than the bottom layer, we can integrate that pressure and get our resulting force, which is a force basically directed to the ground, and that's the downforce we're generating. The steps in order to calculate the forces are the following. First, we need to generate cell normal vectors. These are normal vectors to our surface. Then we calculate the product minus p times n on the x-axis and the n about the y-axis. This will get us the downforce and the drag resulting forces. After integrating the variables on the surface of the rear wing, we obtain the resulting drag and downforce. You can draw the curves that every engineering professor loves to see and interpret the results. As you can see, at 250 kilometers an hour, we went from 71 kilograms to 28 kilograms of force, and we get 60% less drag, and that's huge. This will allow the car to reach higher top speed. In a 100 km per hour corner, the car will have 49 kilograms of downforce instead of 26 if the rear wing was open. The fact that we simulated this in different speeds allows us to predict the behavior of the rear wing in different racing scenarios. This will allow us to change maybe the angle of opening of the rear wing, or change maybe the size of it, the dimensions, and everything else. It allows us to actually improve the wing and try to reach better performance from one design to the next. That's it for today. I hope in the next videos we will dive deeper into these kind of subjects. For today, it's just an introduction, so thank you for watching and staying until the end.